Good afternoon, everybody, to a very drab Heidelberg for those of you who are online. Nevertheless, this is definitely the place to be, and in more ways than one, a very hot place to be, because we're going to hear today from, I guess, the greatest expert that I've ever met personally on the topic of magnetic field propagation of particles and the solar physics. And let me just pass straight across to Brian to introduce Jim Drake, who is our speaker.
Thanks, Richard. So it's a real pleasure today to introduce Professor James Drake, who's been joining us here from University of Maryland. So a quick summary of Jim's career. So he got his PhD, his undergraduate PhD, completed in 1975 from UCLA. And after a short period there as a postdoc, moved to University of Maryland, where he rose up through the ranks, where he's now a full professor at the University of Maryland, which is really one of the leading institutes globally in terms of plasma physics in general. So Jim's focus has been a long and productive career. His background or his earlier work was more focused on tokamak plasmas and particle transport in general. And via one way or another, he wound up looking at magnetic reconnection, particularly in the context of heliospheric and solar physics, magnetic reconnection, and around the Earth's bow shock magnetotail. And he's really established himself as to my mind, the expert on the topic, really making the most dramatic and most impressive and consistent works on this topic. So I think with the latest results coming from Parker Solar Probe, this is really revolutionizing our understanding of what's happening, and I think Jim is going to give us a really thorough overview of that. So I think we're in for a real treat. I should mention that Jim has received multiple awards throughout his career. He was a Humboldt professor here in the early 90s, has won awards for his outreach, I learned recently as well, and has won the Maxwell Prize, the James Clerk Maxwell Prize, which is probably the most prestigious award that you can receive in the field of plasma physics. So it's a pleasure to have you here. I've really enjoyed talking with you for the last 2 days, and I'll hand it over to you now.
Thank you. Sure, I have to say that I have never been to Heidelberg before, and so when I got this invitation, I've always heard great things about this city, so I really sort of wanted to see it all. So I'm really happy to be here. So yeah, I'm going to talk about some of the recent observations from the Parker Solar Probe mission, and which is turning out to be, I think, producing some remarkable results. And so I'm not going to cover, of course, everything that Parker has discovered, but some important stuff about the solar wind. And this first slide just shows you a picture of the spacecraft. And this is the only one I have in my talk. And I guess importantly, as you can see, the heat shield. So the heat shield has to face the sun, and the instruments are back behind the shield. And so you have to be careful sometimes, because if Parker is going too fast as in Italy, then sometimes you don't get all the particle data because everything is sort of behind here, behind that heat shield. And so then the probes to the electric field and magnetic field sort of stick out into the solar wind. And so anyhow, here's the spacecraft. Anyhow, I will say something more about the mission as we go on, but I figured you guys would want to see a picture of what the thing actually looks like. Okay. So first of all, observations throughout the universe reveal high velocity winds of plasma and magnetic field, and these are produced, of course, by the sun, but also from stars, pulsar nebulae, and other compact objects across the universe. And it's just some nice pictures. Of course, we can't do a picture of our own heliosphere because we're sitting in the midst of it, but we can certainly see the wind structures from other stars. Anyhow, the Parker Solar Probe mission was designed to I lost my cursor here. Was designed to probe near in the near coronal solar environment down to around 10 solar radii, and to identify the mechanisms that produce the hot corona, which is around 100 eV, and drive the solar wind. So that was the goal of the mission. So I'm going to start off by just talking about a few basics about the solar wind. And since I'm going to bring up the topic of reconnection, I'm going to show a couple of slides talking about reconnection and what it's all about. And then we'll get on to looking at some of the Parker Solar Probe data that is provided us some important clues about what's going on in the surface of the sun. So the basic structure of the wind is shown here from the Ulysses spacecraft. And you can see that there's, the way this plot goes, it's got the velocity of the wind horizontally and vertically, and then this is as a function of latitude. And you can see that the slow wind, which is maybe 400 kilometers per second or so, is in the equatorial region. And as you go up to high latitude, you hit the fast wind, which is closer to 700-800 kilometers per second all around. And then again, on the southern side, similar structure. So this is the structure of the wind. And we're going to be talking about the fast wind. And importantly, the fast wind arises from coronal holes. And so I'm going to show you now, just to remind you about coronal holes. So there are dark regions of this on the surface of the sun. So here's a coronal hole. Here's a coronal hole. And if you look, so the coronal holes are regions of nearly uniform or that have a dominant component of the magnetic field, which is in one direction. And these are open field lines. And if you look over in these pictures over here, then you can see what happens. These open field lines spread out and expand and basically form most of the wind here on the northern side and here on the southern side. So the coronal holes basically control the magnetic structure throughout most space in the near solar environment. And these things are typically low density, and so they appear very dark here. But anyhow, the magnetic field from these coronal holes fills the magnetosphere, and so this fast wind then occupies a large part of the space around the sun, especially during solar minimum. Okay, so let me say something about reconnection now. Before I start showing the Parker data. So here's some of the basics. So if you have a reverse magnetic field here like this, and then you break this magnetic field and cross connect it over here, then you'll get the bent magnetic field like this and bent magnetic field like this. And what drives the reconnection process then is a tendency for this field line, which acts like a rubber band. It wants to expand outwards in slingshot behavior, and it drives then, as it expands outward, it drives an outward flow, which is the Alfvén speed, to the right and to the left. And if you think about it, if you have a flow, the flow out to the right and to the left, there will be a low pressure region in the middle, and that low pressure region pulls in the magnetic fields from either side, and then brings this field line in, and then it reconnects. So this release of magnetic tension of the reconnected field line is what drives the reconnection process. And importantly, this is a self-driven process. There's a mythology or thought process in the field that you have to push these field lines together, but that's not the case. Magnetic reconnection is self-driven. Okay. So let's talk about some of the characteristics. The magnetic energy release takes place dominantly downstream here. So here's the reconnection site. And downstream, you have these bent field lines that are expanding outwards. The magnetic energy release does not take place here, where reconnection occurs. it takes place in the downstream region where the magnetic field relaxes its tension. So this is the energy release zone for the magnetic field. There's a characteristic energy release, which is the available magnetic energy per particle, and that's given by this expression here. So B squared over 4 pi is the pointing flux that's coming into the reconnection site, and then you divide by the density. This is the energy per unit per particle during reconnection, and that's simply given by mCA squared, where CA is the Alfvén speed. So this is a key parameter that you want to look at if you're trying to figure out how a plasma gets energized. And so, for example, in the corona, mCA squared varies from about a 1 to maybe 20 kilovolts. So, and what that means is, of course, this is not relativistic in the sense that the Alfvén speed is not relativistic. And that differs somewhat from pulsar magnetospheres and this sort of thing where you can have the Alfvén speed approaching the velocity of light. The other thing to recognize is that if you look at reconnection in a very large system, it's not a laminar type process, it's highly bursty. And just here's an example from some MHD simulation of the reconnection process, and you can see all these secondary flux ropes which are forming in the current layer. If you project to a realistic system like the sun, a very large system, there should be thousands of these flux ropes within a current layer. So reconnection is not a simple laminar process. It's going to be highly bursty with hundreds, if not thousands, of flux ropes in the current layer. Okay, so the next thing I want to talk about is interchange reconnection, because that plays a fundamental role in the Parker observations. So let me describe to you what that is. Interchange reconnection is reconnection between an open flux region, and I don't know if you can see this here, but there's arrows pointing downwards here, yeah, and arrows pointing upwards here. And the reconnection takes place between closed flux. So this is closed flux, which is supposed to be on the surface of the sun, and an open flux, for example, in the coronal hole. So this flux reconnects between these two, and then you form a field line that looks like this. And then outwards from this reconnection process, you see this bursty patches of stuff going out and upwards in a vertical direction. So this is interchange reconnection. And one thing to note is that you look at these field lines up here, they're all pointing in the same direction. So unlike traditional reconnection in which you have a reverse field like this, the outflow flux of plasma along these field lines is on unidirectional field lines. Now the reason this is called interchange, because if you look at this picture here, you started off with a field line whose foot point was here, and then it reconnects, and lo and behold, the foot point is over on the other side over here. So it changes the position of the foot point of the field line. So the original idea behind interchange reconnection was developed by Len Fisk in 2005. The idea was to understand how magnetic flux, how open magnetic flux diffuses on the solar surface. And so this was a major new understanding, because now you change the foot point from here to here, you're effectively diffusing the position of the open flux on the sun. Anyhow, so this is interchange reconnection. So keep this picture in mind as we go through this. So let's now talk about solar wind modeling. So Eugene Parker first predicted that the pressure from the hot corona would drive a supersonic outflow. And of course, when he first proposed this, it was highly controversial. Nobody believed it at all, until, of course, his predictions were confirmed by Mariner 2 observations in 1962. If you then start looking at the various models that arose afterwards about what drives coronal heating and what drives the outflow and to make up the solar wind. There's this so-called furnace model in which you have magnetic reconnection in the chromosphere, and the idea was, so here we are, sort of a high density region in the sun, there's magnetic reconnection going on, and the idea was that reconnection then would drive Alfvén waves. So here's a kink-like structure supposed to represent an Alfvén wave, and those waves would propagate up into the corona and heat the corona, and that would provide the energy required to drive the outward solar wind. So this was the original idea. There was also models in which they said, okay, there's the convection zone down here, convection zone twists up the magnetic field, and this convection zone could also produce Alfvén waves that then could heat the corona. So the dominant mechanism for driving the wind has always been, over the years, the idea that there's Alfvén waves up in the corona that are heating the corona and driving the wind. Okay, so what about the possible role of magnetic reconnection instead of in the chromosphere in the low corona? And so this was provoked.
Yeah, Parker Solar Probe was launched from the Earth, and the first pass around, it got to about 35 solar radii. And what they've been doing over time is the spacecraft has come into perihelion and back out again, and it comes and flies by Venus, and they use the Venus interaction to tweak the trajectory. So anyhow, they've been tweaking the orbit, and now Parker Solar Probe is down within inside 12 solar radii. And there's a full complement of instruments: magnetic field, electric field, particles for over a very large range of energies. And so the spacecraft trajectory and the heat shield sometimes cause issues in terms of whether you're measuring the full spectrum of particles, but it's pretty good. So so one of the first important observations from the Parker mission was the observations of magnetic field and a very bursty magnetic field as you got close to the sun. And so here is the radial magnetic field. Here's 0, by the way. And here is the conventional 1/r² fall off, which you expected, which looks sort of like this. But when you start getting close to the sun, you see the magnetic field becomes extremely bursty. And again, you see the 0 line here. And so these bursts actually cause reversals in the direction of the radial magnetic field. And so these things are called switchbacks. So these were the first papers were published in 2019 on this. And what actually is producing these switchbacks continues to be discussed, and there's lots of papers going on. But anyhow, you can see this artist's picture of a switchback. So here's the magnetic field, and it's got a kink in it, comes out, and then Parker is measuring that kink. So the magnetic field close to the sun is becoming very turbulent, with large amplitude reversals and fluctuations in the magnetic field. Okay. So when the spacecraft got within around 20 solar radii, they started seeing something very different. And you can see here is the magnetic field as a function of time. And here is the radial velocity as a function of time. And you can see that the switchbacks here are starting to undergo modulation. So there's a modulation here, modulation here. So you see very bursty switchbacks, but the amplitude is getting modulated. And the corresponding flow velocity, radial flow velocity of the solar wind plasma is also modulated. And lo and behold, if you take these modulations and project them back onto the surface of the sun, the periodicity of these modulations match the periodicity of the magnetic field on the solar surface. In particular, Here's the measured surface magnetic field on the sun. You can see it's multipolar. Red and blue means that the magnetic fields are going up and down. This is within a coronal hole. So even though the coronal hole has a dominant magnetic field direction, it is very, there's a multipolar behavior. So there's positive and negative values. So it has these closed loops, as I was talking about before. So coronal holes are not single unidimensional magnetic fields. They have multipolar magnetic fields at their base. And you can see here that if you look at the magnetic field from starting with the surface and you do a model, this is the spatial structure you get as a function of altitude. And then you look at the measurements of the velocity from Parker Solar Probe projected down onto the solar surface. You can see the periodicity here matches the magnetic periodicity on the surface of the sun. So these modulations are linked to the supergranular scales on the surface of the sun. Now, on top of this, if you look up here, I don't know how well you can see this, but these are energetic particles measured as a function of time. And the highest energies are somewhere around a little bit less than 100 keV per nucleon. And so what we're seeing here is that the wind is not a hot thermal wind that comes out. It has a energetic component. So the solar wind is not simple hot thermal plasma coming out. It is a wind that has an energetic particle component to it. And I'll show you a little bit more about the spectrum as we go along here. And if you project down to the magnetic field from the Parker Solar Probe, it projects down to around 4 Gauss, and that sort of matches the strength of the magnetic field, which actually measured by the SDO spacecraft. Okay, so these characteristics of these modulations link up very nicely with interchange reconnection as the driver of these bursts. And so, for example, you see bursty flows on top of an increased ambient solar wind, and we expect those bursts from a reconnection process, as I was mentioning at the beginning. Reconnection is expected to be bursty. There's increased plasma density within these bursts. I'm not showing that here, but the bursts have higher plasma density, and they have higher pressure in these regions. They have reduced magnetic pressure. The magnetic pressure in these regions is also reduced. They directly measured that. And you see these bursts of energetic ions, as I was showing up here. And these are all signatures that you expect from an interchange reconnection process. Okay, so here's the picture. Now, keep in mind that these flow measurements from remote observations that I showed you earlier, those observations you sort of saw sort of spatially isolated bursts coming out from the sun. However, these observations suggest that, in fact, the reconnection process is essentially continuous. And so what do I mean by that? So here's an example. We have a closed flux regions here, and we have open flux. So imagine that you're reconnecting this open field line here with this closed flux region here. So here's the reconnection site. So what happens? This field line reconnects. Here it is bent here. And then as it straightens out, it shifts to the left. So this reconnected field line is now shifting to the left. It's straightening out. It's shifting to the left. It's shifting to the left. It's now fully straightened. And now it starts interacting with this other closed flux region. So reconnection then happens here. And now it's straightening out again. It's shifting to the left. It's going to the left. This is what Parker Solar Probe seems to be seeing. It's seeing these outflows where you see a periodicity, where you see flows coming out here. But the reconnection process seems to be continuous. It's not these isolated events. As far as we can tell, it's a continuous process similar to what that picture shows. Okay, so, and in particular, what we started looking at on the simulation side was to see if we can figure out what these outflows look like. So I showed you this picture here before. And one interesting thing is if you look at a spacecraft perhaps crossing here, then a newly reconnected field line, which is right here, what are you going to see? You're going to see high-speed flows coming out, and this spacecraft would see those flows. And then if you go to further to the left here, this field line reconnected a long time ago. So all of the high-speed flows have already gone by here. So the spacecraft, when it hits this point, is not going to see as many high-speed flows because that stuff has already gone and passed out. So what do you expect to see? As you enter this exhaust, what you expect to see is bursty, very high-speed flows, and then the flows would get smaller and smaller until you go to the other side of the exhaust. And look at what you see in the observations. You see as a function of time, you enter this region, you see very high-speed flows, then they die away like this. So you see an asymmetry in the signal of the flows, and this is what they see directly in the data, and that's what you expect to see from the reconnection process. So the asymmetry that they measured seems to be consistent with the spacecraft crossing into an exhaust region from interchange reconnection. Okay, so taking the data from PSP, we tried to project down to see what we could figure out about the reconnection process in the low corona. So the first thing we did was to project the magnetic field down to the corona from around 300 nanotesla at 13.4 RS, which was the radial position of the previous data. And it projects down to around 4 Gauss at the solar surface. And that's consistent with the solar surface magnetic field measurements. So those magnetic fields match. The magnetic field at the spacecraft maps down to around 4 Gauss, which is what they actually measure with the Solar Dynamics Observatory. If you look at the flow bursts at PSP, the bursts are around 300 kilometers per second. And if you argue that that 300 kilometers per second should be roughly what the Alfvén speed is in the reconnection process at the solar surface, because the bursts during interchange reconnection are going to be Alfvénic. So if you take that 4 Gauss magnetic field and then you say, well, what's the density if we have an Alfvén speed of 300 kilometers per second? It comes out to around 10 to the 9, which is consistent with what you expect from the density in coronal holes. Perhaps one of the interesting questions is if you ask, well, what is the reconnection inflow velocity down in the low corona? In particular, so there's reconnection going on, so there's going to be inflow that a velocity of that inflow, which is the reconnection speed. Can you figure out what that might be? And the idea is that that we came up with is that if you look at the spacecraft position about 10 solar radii, what you see is in the observation of data is essentially continuous reconnection. In other words, you don't see a system where you see a burst of reconnection and then essentially nothing, and then a burst of reconnection. That's what you would expect to see if the spacecraft, if the velocities from the reconnection process were on a shorter time scale compared to the crossing time, then you'd expect to see a burst here and then everything dies out and then another burst, but that's not what you see. And so based on these observations, it seems as if the transit time of these bursts to the spacecraft is comparable to the rate at which the flux is being reconnected on the surface. And if you make that argument, then you find a reconnection inflow velocity, which is about 3 kilometers per second. That's about 1/100th of the Alfvén speed. So our best estimate for the reconnection inflow velocity is around 100th of the Alfvén speed, around 3 kilometers per second. If you take that reconnection inflow velocity, put in the density and the temperatures from that, then it turns out that the reconnection electric fields exceeds the Dreiser runaway field by many orders of magnitude. In fact, nearly 3 orders of magnitude. So that says that collisionless, surprisingly, seems to be collisionless. And that's consistent with the fact that you're seeing all these energetic ions. You're not seeing a thermal distribution of ions. You're seeing very energetic ions. And then if you go back and you say, okay, what's the rate of energy release just from the reconnection inflow velocity and the magnetic field strength, you get around 5 times 10 to the 5th ergs per centimeter squared per second. And that is sufficient with the estimates people have made to ask whether you can actually drive the wind. That is efficient energy release rate. Okay, so let's talk about the fact that we have an energetic wind. So this shows the spectra of energetic particles measured by Parker Solar Probe. And you notice that, so here's the protons here. You know, there's a gap here. That's because of the instruments. There's the ESIS instrument over here at high energy and the SPAN-I instrument here at low. And there's unfortunately a gap between those two, but if you connect them, it looks like a pretty nice power law here. And here's the helium ions. So we carried out simulations of interchange reconnection with a particle and cell model, and then we calculated the spectrum we got from that, and this is what we get. And so the power laws match, the slopes match really nicely. And if you look at a PIC simulation of this kind of thing, there's a free parameter, and that free parameter is this parameter MICA squared or MIVA squared. Remember I mentioned that at the beginning, that's the available energy per particle. And that's a free parameter in the PIC simulation. We could pick that to be anything we want. So what we did was we said, okay, let's match the low energy edge of the proton power law spectrum with the low edge of the power law spectrum in our PIC model. And if you equate those two, you get MCA squared of 1.4 keV. And that corresponds to an Alfvén speed of around 370 kilometers per second. So that's consistent with that earlier estimate I gave you, which was that the fluctuating velocity was around 300 kilometers per second. So we have two independent ways of estimating what the Alfvén speed is in the low corona where this energy release is taking place. So anyhow, the solar wind is an energetic wind. It has a component which has got energetic ions, including protons and alpha particles. Okay, so reconnection seems to be happening in low corona. And the question is, how does this reconnection process drive the solar wind? So first of all, you have a bulk Alfvénic outflow that forms the reconnection exhaust. You have direct deposition of magnetic energy into plasma pressure and energetic particles. So there's a pressure there. So it's not just a bulk outflow, there's pressure. And then, of course, there's a possibility that you can have MHD turbulence produced during the reconnection process. That turbulence, in particular Alfvén waves, could act, produces a Poynting flux, and then that could also act as a source of coronal heating. And of course, that's what historically people have believed was the dominant heat mechanism for heating the corona was that in fact, that Poynting flux. However, so here's where the controversies start, okay? And that is that if you look at observations in the Earth space environment measured by in situ satellites, then the MHD pointing flux from reconnection is much smaller than the bulk flow kinetic energy and the ion enthalpy flux. So this is well established in the Earth space environment. There's very little energy coming out as pointing flux and Alfvén waves in the Earth space environment where they directly measure reconnection. So, and our PIC simulations also reveal that there's very little energy coming out as pointing flux from the reconnection process. So the question, a fundamental question is whether reconnection in the low corona actually produces the expected Alfvén waves that everybody's been using for many years to heat the corona and drive the wind. So that's a question which I think is up in the air. And so the first thing I'm going to show you then is if you just say, okay, let's just look at the bulk outflow and the ambient plasma heating as the dominant solar wind drive. Let's discard the pointing flux and see what the consequences are. Okay, so let's look at the bulk Alfvén speed and the ambient heating from reconnection and see if we can drive a wind from that. So the reconnection energy per particle is again given by MCA squared. That's the available energy per particle. Typically half of that goes into bulk flow kinetic energy, so that's this. So half of it goes into bulk flow. The rest of it goes into thermal energy and energetic particles. So I'm going to set half mv squared equals to 3/2 t. And that gives you a sound speed, which is given here. It's a fraction of the Alfvén speed. And note that the sound speed is less than the Alfvén speed. And that is an important ratio. And it turns out you have to have the sound speed less than the Alfvén speed to actually produce the wind solution. Okay, so let's take these energies and see what the consequence is. It turns out that if you're throwing away the Alfvén wave heating in the corona, then there's a Bernoulli-like equation which you can immediately write down. 1/2 v squared plus pressure and then the gravitational potential energy. That is a constant. And then you say, okay, let me plug in the Alfvén speed squared, and I'll plug in that pressure that I had on the previous slide and see what we get. And then you have to demand that that has to exceed this gravitational potential energy. This has to be positive, otherwise you're never going to get a wind solution. So you put all that stuff in, and lo and behold, you find that the minimum Alfvén speed required to get a wind solution is given by this equation here. And it turns out to be 377 kilometers per second. Keep in mind that the escape velocity of the sun is 615 kilometers per second. So in order to have a wind solution, you certainly don't have to have the Alfvén speed comparable to the sun's escape velocity. But any Alfvén speed of order, say 350 to 400 kilometers per second, is sufficient to drive a wind solution. Okay, so we then proceed to try to see if we can match the characteristics of reconnection at the solar surface and project that all the way out to where Parker Solar Probe is at around 12 solar radii. And so you can integrate those solutions outwards using a realistic magnetic field profile that you get from a coronal hole. And keep in mind, that's a very rapid expansion outwards. It's not simply radial. You take the magnetic field expansion from a coronal hole and then put that in and integrate the equations out. And you find that the density profile looks like this, and the magnetic field profile down below here. And then you can calculate the profiles of the flow speed, the radial flow speed, and the Alfvén speed, and the sound speed. And now we've matched these At Parker Solar Probe, the Alfvén speed is around 100 kilometers per second. If the sound speed is lower, and you have a high-speed wind at around 400 kilometers per second. Okay, now you look at these profiles, and they're very different from the historical profiles that everybody is used to seeing, because you see a very rapid increase in the velocity. And the typical profiles that you have gotten from a conventional Alfvén wave heating models have the velocity coming up around 8 solar radii or something like that. So you get a much more rapid increase in the velocity coming out from a reconnection exhaust than the conventional profile of the wind speed. Okay, so one of the consequences of a reconnection model driving the solar wind is you don't expect to see a smooth solar wind. Reconnection is highly bursty, so you expect to see a highly structured wind. And so, for example, if you integrate the equations out and you look here at, suppose you start off with a high velocity injection from a reconnection site, and then adjacent you have, or even temporally, you have a much lower velocity, and you calculate how that evolves in space. You get a high velocity here, but then this velocity here fails to form an outgoing wind solution because it didn't start with a high enough velocity, so it plunges down, and you fail to form an outgoing wind solution. So what do you expect to see in a reconnection drive mechanism? You expect some regions with a nice outflow wind speed, and an adjacent region in which it didn't quite make it. So what's the consequence of that? The consequence is an enormous amount of free energy, because now these relative velocities exceed the Alfvén speed. And that means there's a lot of free energy that could potentially drive turbulence. So what I'm getting at here is you expect in a reconnection drive model, you expect a highly bursty solar wind coming out with a lot of spatial structure. And that spatial structure is a source of free energy that can drive turbulence. And so we've started to try to look at that to see if that can explain the turbulence measured by Parker Solar Probe, and in particular, the switchbacks. And so in this is a PIC simulation then of some high velocity streams coming out. And this plot here is the radial magnetic field. And you can see when you see regions of blue, the magnetic field is actually reversed. So the regions of blue there are locations where the field is reversed. So those are nominally switchbacks. And you see a very large out-of-plane magnetic field, which is typical of what you see in the switchback. In a switchback, what you have is a radial magnetic field undergoes a sharp rotation like this, and then back again with nearly constant magnetic field strength. And that's what you see in this kind of simulation. So, what we're trying to look at here, and this has been by no means now well established. We're trying to look and see whether the highly structured solar wind with free energy associated with the relative streaming of beams, is that really the source of the turbulence that's measured by Parker Solar Probe, and is that the source of these switchbacks? And that's still an ongoing topic. Okay, so I'm coming to my conclusions now. So the bursty behavior of the solar wind by Parker Solar Probe close to the sun is consistent with the crossings of interchange reconnection exhausts. Reconnection simulations of interchange reconnection reveal power law distributions of protons and alphas with power laws that are consistent with SPAN-I and the ESIS data. So the solar wind has an energetic component which seems to be produced by the reconnection process. The alphanic outflow combined with ambient heating from interchange reconnection near the solar surface is sufficient to drive the fast solar wind. However, the profiles of reconnection outflows differ greatly from the conventional wisdom. And I think the relative roles, so I think the big uncertainty now is concerns the relative roles of direct coronal heating from reconnection versus reconnection-driven alphane waves, which give rise to heating higher in the corona. So this is an open question, which I think everybody is still arguing about back and forth. The bursty behavior of reconnection drives a highly structured wind with enormous free energy. And so this is one possible source of turbulence. Of course, the possible resolution of these two issues is that the bursty reconnection behavior could be the source of these alphane waves. And so maybe it's the interaction between these bursty outflows and the resulting production of alphanic turbulence that actually is really the source of heating in the outer corona. This is still to be explored. And so this is one of the things we're continuing to talk about and trying to figure out. Okay, so thank you very much.
Well, thank you very much for that beautifully insightful talk. I think many of us who are not experts in this field really appreciate your insight into these new observations and their explanation. We have an online audience. I invite them to type messages into the message box. And in the meantime, please, let's start with the questions from the hall.
Thank you. Did I understand it correctly that the timelines of the magnetic field you see are just a reproduction of a flyby of a solar probe? Okay, and you've shown the Bale-like simulations in the last step. Are the sizes of the regions comparable to what you have seen in solar probe?
So wait a minute, I'm confused. Can you repeat the question?
Yeah,
I'm not
so
sure.
I understand that.
Oh, so we're talking about the Parker data now?
First the Parker data, I understood that the Parker data is not a timeline of a magnetic field, but it comes from through the flyby of a satellite through the magnetic field on the surface, right? And now my question was, if I compare that with the simulations you've shown in a later stage, can we compare the sizes you have inferred from the solar probe data to the simulation?
Yeah, so these match. The density matches and the magnetic field matches. So here we are at Parker Solar Probe. These match the Parker Solar Probe.
I meant the size of the regions.
Yeah, the size of the region match.
Okay.
Yes, they do. I mean, that was the first point, is that the periodicity measured by Parker Solar Probe, when you project that down to the surface, exactly matches the periodicity of the magnetic field on the solar surface.
One short tiny technical question. You've shown the spectra from the particle cell simulations. How many particles per cell did you use?
About 100. Yeah. For the PIC simulation. Yeah.
Okay, another question.
We didn't use one particle per cell.
Christian Fent.
Well, a lot of people use one particle per cell, but we don't.
I have two questions, actually. One is connected to this plot to the right. So I don't understand this profile of velocity, because a fast gas follows a slow gas. So there should be a shock, you know. So it could not be a steady solution, and you will produce shocks anyway along this streamline. This is fast speed at smaller radii.
So you notice that the velocity always exceeds the sound speed over that entire region. So there's no shock crossing.
Yeah, but at radius 2, you have a higher speed than at radius 6. So that material will will
So in other
catch
words,
up
there's
with-
no
catch up with the
crossing,
slow-
there's no crossing point between V and the sound speed. So this is supersonic everywhere. And the Alfvén speed actually plays no role in this one-dimensional propagation problem.
maybe there's a misunderstanding. Alone from V, alone from the upper curve.
Yeah.
There's gas moving at 500 kilometers per second at
Yeah.
radius 2. And then you have gas at radius 8 moving with 400 kilometers per second only. So the faster gas will catch up the earlier gas and will shock that, no?
So the equations described are in an expanding flux tube, and they're steady state solutions. So I just integrated the steady state equations to get that answer.
Good. The other question was about resistivity. You didn't mention that, and I'm working on reconnection as well
Yeah.
a bit. And this is, for me, it's a free parameter. So can you derive or estimate the resistivity from your solutions? I mean, does it change along the solar wind or?
So keep in mind that the only place where an effective resistivity will play a role is down where you're doing interchange reconnection during that region. So the propagation out across here, of course, resistivity does not really play any role at all. So in our PIC simulations, it's a PIC simulation. So there is no explicit resistivity in a PIC simulation. So it's the dynamics of electrons and ions at the reconnection site which controls the rate of reconnection. And that reconnection is fast, but it doesn't require the addition of any resistivity at all.
And you cannot derive from that parameters effective, efficient.
We can produce an effective resistivity.
Exactly,
Yes,
yeah. Okay.
yes, we can. But it's not really a resistivity, and I'm saying that because a classical resistivity will do a lot of dissipation of magnetic energy as opposed to driving flows and energetic particles. So it's not clear that parameterizing it as a resistivity is a good idea.
Thank you.
We have an online question from Keith Stillerond. Now I'm going to turn on the volume here and see if Keith can put the question directly through the microphone. So go ahead, Keith.
Okay. Yeah. So from my understanding, so you have this.
I don't hear anything.
You don't hear anything? Okay. Hello? Can I try it again?
Okay. Sorry, Keith. I'll read the question out since we don't hear you. Keith asks, for my understanding, here it is, periodicity scales of magnetic field on the surface, do they correspond to the typical scales of granules convective cells?
Yeah, it's a supergranule scale. So if you look, so this picture shows, so this is the supergranulation scale, and so this is from the surface magnetic field measurements. So this is the characteristic scale there. And then oh, no. Didn't I show? Yeah, here. So here is the, this is from a so-called PFSS model of the magnetic field as a function of altitude and longitude. So this is the measured scale from the solar surface. And this is the projection down of the measurements by Parker Solar Probe down to that region there.
Okay. He's asked, so that, yes, no, I think that, so that is the scale at which the reconnection occurs, right, on the
That's
granular
correct.
scale. Keith has added, so that is the scale at which the reconnection
Yeah,
occurs.
so our argument is that it's the reconnection process on this scale. Now keep in mind that what do you expect to see if you're reconnecting this, say, closed magnetic. So here's the flux
I don't remember whether this is positive or negative, but it doesn't really matter. Suppose it's positive and that's negative, and it's so there's the reconnection between some open flux here and that downward flux region. That reconnection process defines the scale here, which is this supergranule scale. So that defines a scale across here. Within that scale, there's a highly bursty flow, which is smaller than this scale. So the bursts that you see here are below the supergranulation scale, but this overall profile is the supergranulation scale, which is shown over here.
Okay, I think, yeah, Keith says thanks. So last question, I think, oh, two more questions. I think Brian got in first, so start with Brian.
Thanks again, Jim, for the really nice talk. So the picture of this interchange reconnection seems very 2D, of course. It's understandable.
Yes,
So
right.
if these closed field lines were in fact twisted flux tubes, would that change the situation? Because the field lines at the base wouldn't be able to cross, or do you not expect them to be twisted at all?
So yeah, so one of the things we're talking about is trying to do a simulation in which we get rid of this two-dimensional model and ask, suppose you have realistic flux on the solar surface, which is clearly not two-dimensional, and then but you still have open flux. So how is that open flux gonna try to migrate through the closed flux regions? And of course, that's a very interesting topic. And we really haven't explored that yet, but our plan is to actually do that. Yes.
Okay. And then follow-up question: why would the slow wind be any different? It's almost certainly the same physical processes occurring.
The slow wind seems to come about there's these helmet streamers, which are at low latitude. So in the helmet streamer, you see a closed field line region, which tends to break off near the top, probably due to heating within that closed flux region. And so there's a periodic outflow. So, I mean, it's still probably a reconnection process, but the density is much higher. And I think that's probably the difference, because in the coronal hole, the density is rather low. And so if you have a release of magnetic energy, you're going to be able to get a much higher outflow velocity. I think the density is higher in the slow region. I think that's the biggest difference.
In the first sketch you showed of reconnection, you have this very symmetric picture. Yeah. But in the interchange reconnection, it's usually rather asymmetric.
Yes.
All the flux is going
Yes,
out.
definitely.
But if I look at this picture here, I can see that the tension of the magnetic field is going to drive some energy flux into the surface. Yeah. Is there a way of detecting that, or is it comparable to the energy release?
Okay, so this is a very interesting topic. And in particular, when we first started doing the model where we projected what we thought was going on the surface out to solar probe, this first projection, if we took the 10 to the 9 density and tried to project that outwards by integrating those equations, we found that the density at Parker Solar Probe was almost 2 orders of magnitude too large. And so that, we concluded from that, if you look at how much flux was actually going to be driven outwards versus that which is going down to the solar surface. So for example, here. So keep in mind that so here's the PIC simulation. This is the outflow coming out here and the downflow here. But lo and behold, if you look at the field lines, these field lines here are connected around over here. And if you look at a corresponding plot of the density, most of the plasma actually comes up over here and then back down again, as opposed to going out. So only a small fraction of the density actually gets out here. And it's not shown very well in this plot, but I have another plot showing the density, and the density actually is mostly going along down back into the foot points. So yes, you're exactly right. A lot of this stuff goes down, it doesn't go out. Whether you could see X-rays, I don't know if there's enough energetic electrons to see this, but
I've had some discussion with some of my colleagues who are trying to argue for a new satellite mission with the Foxy spacecraft, which could measure energetic Bremsstrahlung. And the question is, would you be able to see modulation of the soft X-rays, for example, that are linked to this periodicity? And I think that's a really important question. And if they could actually see that, I think that would be a big step forward in trying to correlate with what Parker is seeing.
Okay, well, interesting to see so much energy going back down onto the sun after all those things. Well, before we thank Jim, I have a couple of announcements to make. First of all, next week's speaker will be Alexander Hager from Monash University, and he is still mulling over the topic. It's either going to be massive star evolution and nuclear synthesis in the first stars, or it's going to be something completely different, which is collisions of asteroids and the formation of Arrokoth. So if you have any real strong views on that, do get in touch, please, and let me know. And in any case, we do look forward very much to the visit of Alexander Hager next week. And I think I'll just pass over to Brian, who's going to just say something about dinner tonight.
Yes, so just to make a reminder, there will be, Jim has kindly agreed to join with students for private question Q&A session. If you want to ask any questions without your supervisors listening in, we promise not to have secret recordings. And then if you're interested in joining for dinner later, we're going to go to the Kulturbrauerei at 7:30, and you're welcome to join. So thank you again, Jim. Thank you, everyone.